D block elements, and we have 2 more compounds, okay, potassium dichromate and potassium permanganate. Before that, discussion in property wise, the last one is oxidation state. Okay. We know that D block elements can show variable oxidation state. Fine. Oxidation state, the first point, shows variable OS. Shows variable OS. Show variable oxidation state. Okay. Why they shows a variable oxidation state? Because this is actually outer electron, right? And this is the inner one. And the energy difference between, listen, energy difference between Ns and N-1d comparatively low. So even if it is inner one, it can also act as valence electron. Normally the valence electron is the electron from the outer shell, right? Which means the ultimate shell, which means Ns. Okay, but the energy difference between Ns and N-1d are comparatively low. It is clear that energy of N-1d, that is little greater than what? Energy of 4s or 3d is much. Which one have greater energy? 4s or 3d? 3d have greater energy. This is Ns and this is N-1d. Ready? Even the 3d have greater energy than 4s, but this energy difference is low. Okay, so electron can ionize from 4s as well as 3d. So for transition elements, the valence electron, which is from Ns and N-1d, so it can show a maximum as far as possible, or maximum possible oxidation state. Okay, and we know that, you know that in your redox reaction it is discussed, the element with the maximum oxidation state is ruthenium and osmium, and it is discussed in your redox reaction. Okay, so this is nothing but this is a transition element. Okay, element with a maximum oxidation state of for an element in a periodic table, that is +8, and it is shown by your transition elements. Okay, fine. So the first point, they can show variable oxidation state because this is 4. Okay, because Ns and N-1d orbitals orbital can act as valence electron, or orbital electrons can act as Ns, or N-1d orbital electron can act as valence electron. Okay, ready? In bracket, energy difference between Ns and N-1d low. Okay, energy difference between Ns and N-1d is low. That's the reason. Ready? Okay. Next, first point. Next point I do. In 3D series, and there is the variation of oxidation state in 3D series is given in your textbook. Okay. So in 3D series, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, first scandium can show +3. Ready? Titanium can show +2, +3, +4. Vanadium can show +2, +3, +4, +5. Okay, chromium can show +2, +3, +4, +5, +6. Well, your typical manganese can show +2, +3, +4, +5, +6, +7. Okay. Ready? Where iron can show +2, +3, +4, +6, +6. Beyond your iron, the tendency to show higher oxidation state relatively low. Cobalt can show +2, plus 3 plus 4, where nickel can show the same, plus 2 plus 3 plus 4, plus 2 plus 3 plus 4. Copper can show plus 1 plus 2, zinc can show plus 2. Okay, this is the variation. So element with the maximum possible oxidation state in 3D series is manganese. Okay, and general OS of 3D series, that is plus 2. Plus 2. Scandium hardly forms plus 2. Okay, but it is not stable. Ready? So the general oxidation state is plus 2. Okay. And this is given in your textbook. Okay. So questions maybe from this one also. We'll write the whole points. Okay. So it is clear that from left to right, the tendency to the possibility for showing maximum oxidation state increases, then it decreases, and that is based on the presence of unpaired electron. Okay, the availability of electron, and beyond iron, the tendency to show maximum oxidation state decreases. Okay, fine. Next point: if a metal is in a lowest oxidation state, listen, titanium chloride and titanium oxide, where the titanium is in plus 2. So these compounds mainly ionic, moreover basic, or ionic. They are mainly ionic. Ionic, having a ionic character, and Cl minus having an ionic character. But if it is in a higher oxidation state, like this, if the titanium, whereas the titanium is in a higher oxidation state, have a tendency to form covalent character, moreover acidic behavior. Ready? So we know that titanium can show plus 2 as well as plus 4. Generally, if a metal is in a lower oxidation state, its compounds will be, or if it is next in a lower oxidation state, it will be ionic, moreover basic. Okay, if it is in higher one, then it will be covalent and acidic. So that's the next point, and we can show some examples. Okay, so next point: if metal in the video, if a metal in lower OS, okay, generally ionic. Lower OS ionic, enough. Lower OS ionic, and in case of oxide, it will be basic. Okay, we will discuss the nature of oxide later. Okay, and then we will discuss here. So ionic, example, bracket example, ionic, TiCl2, TiO, they all are ionic. Okay, but if it in higher OS, the bracket, these two are ionic compounds because they exist in a lower OS. Okay, the next that is in higher OS, but if it in higher OS, covalent, having a covalent character. For example, TiCl4, TiO2, or the titanium is the maximum possible oxidation state of titanium. Titanium is in its maximum possibility, so it behaves like a covalent compound. Okay, the next point, that is ready. So next point, if you are moving down the group, the tendency to listen, I think you are familiar with the inert pair effect. Inert pair effect in p block elements. Let I have 14th group element: carbon, silicon, germanium, tin, lead. The group oxidation state is plus 4, right? The group oxidation state is plus 4. And you know the general electronic configuration NS2, NP2. Ready? So carbon readily shows plus 4. But down the group, the tendency to show +4 decreases, where the bottom member can show +2. Okay, germanium can show +4 readily, but on moving down, the tendency to show +2, +4 decreases, and they readily shows the lower oxidation state, +2, which means actually a 2-unit lesser oxidation state. 2-unit lesser oxidation state. Listen, that is, the stability of Ge4+ is greater than Ge2+. Okay, but the stability of Pb4+, that is less than Pb2+. Because Pb is a heavier member. Okay, on moving down the group in case of P block elements, the tendency to show group oxidation state decreases. The tendency to show the group oxidation state decreases, and they readily shows oxidation state which is 2-unit less than group oxidation state, and that is said to be inert pair effect. Where these two electrons, these two electrons become inert. Inert means that not participate as a valence electron. Actually, what is the what is the means here these two electron and these two electron act as the valence electron, right? So for carbon or something like that, or the top member, these all electrons are available, so they can show what? +4. But on moving down, due to screening effect, okay, due to screening effect, these two electrons are screened and it is not available for bonding, so they readily shows +2, and that is said to be inert pair effect. In general, in the case of P block elements, on moving down the group, tendency to show higher oxidation state decreases. Group oxidation state means the maximum possible oxidation state by that group. For example, in the case of 15th group elements, nitrogen, phosphorus, arsenic, antimony, bismuth, the maximum possibility is +5, and that is said to be the group oxidation state. Okay, but in case of any P block elements, on moving top to bottom, the tendency to show the group oxidation state decreases, where the heavier member, down member, shows a 2-unit less than the group oxidation state, and that effect is said to be inert pair effect, where this NS2 electron is inactive or not participating in bonding. Okay, so generally, in case of P block elements, on moving down the group, tendency to show higher oxidation state decreases. But that is the case of P block elements. Okay, moving down, they have a tendency to show the lower oxidation state, not higher oxidation state, on moving down the group. Ready? But in the case of D block elements, if you are moving from 3D, 4D, 5D, or if you are moving down the group, the tendency to show the higher oxidation state increases, where higher oxidation state is much stable than the lower oxidation state. Where the top member, for example, manganese, listen, scandium, titanium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, right? Okay, and lanthanum, hafnium, tantalum, tungsten, rhenium, like that. Okay, so tungsten, which all can exist as +6 oxidation state. The +6 oxidation state of tungsten is much stable. Ready? But the +6 oxidation state of chromium is not much stable. Chromium and tungsten, they all are in the same group. Ready? Chromium, the stability of +6 oxidation state is low, whereas in the case of tungsten, relatively the stability is high. Okay, so it is clear that on moving down the group, the tendency to show maximum oxidation state increases. Ready? So the +6 oxidation state of chromium is not much stable. That's why chromium have a ready tendency to become the lower. That's why the chromium is a good oxidizing agent. Good oxidizing agent. But they all are not. So they all are not much not have a ready tendency to lose electron, because it is stable here. Ready? So the tendency for oxidation also, or oxidizing property also, decreases down the group. Okay, so that's the point. Next we have to discuss about the oxidation state. So Next point. Unlike p block elements, the tendency to show, unlike p block elements, the tendency to show maximum OS increases moving down the group. Tendency to show maximum OS increases moving down group. Okay. So that means that in case of p block elements it is not like that. Okay, tendency to show maximum oxidation state decreases. Ready? But in case of transition elements, the tendency to show maximum oxidation state on down group increases. Ready? In bracket, oxidizing tendency decreases down group, right? Which means the oxidation state of member in the down group is stable. Okay, so oxidizing property decreases down the group. Ready? Example, MnO4 minus and CrO4 2 minus less stable. MnO4 minus and CrO4 2 minus less stable. Okay. Where the oxidation state of manganese is +7, higher one. Here the chromium is +6, higher one. But it is in a 3D series, so relatively less stable. Okay. So the less stable means try to occupy. So less stable means they try to occupy what? Lower OS, which means reduction, which means good oxidizing agent. Okay, ready? So write this also. Less stable, ready? Which means that they try to occupy the lower oxidation state, which means they readily undergoes reduction, so perfect oxidizing agent. The next MoO4 2 minus and WO4 2 minus. MoO4 2 minus, where this is in a +6 oxidation state, this also in a +6 oxidation state. Okay, ready? These are the down members of your chromium, molybdenum, tungsten. Okay, this is in 4D and this is in 5D, where chromium is in 3D. So in 4D and 5D they exist in a maximum possible oxidation state, but this is relatively stable. This is stable. Okay, so stable means they not have a tendency to lower the OS, which means they are not a good oxidizing agent. Ready? Okay, so show this one also. Next point, that's a general point. If a transition metal is in a lower OS, it have a tendency to become higher, so it may act as a reducing agent. Okay, if it is in a higher OS, it may act as a oxidizing. That's a general point which is mentioned in your textbook, so put it as a point. If transition metal in lower OS, bracket Ri reducing agent. Okay, in bracket Ra reducing agent, and this concept is discussed in your redox reaction. Okay, Ra, close the bracket. But if in higher OS, OA. If in higher OS, OA. Okay, next. Highest OS shown by ruthenium and osmium. Highest on OS shown by ruthenium and osmium. Okay. The next point, that is common OS plus 2 like common oxidation state of 3D series is plus 2. Ready? In metal carbonyls, next point, in metal carbonyls, metal exists as 0 OS. In metal carbonyl, metal exists as 0 OS. Example, Ni, and this is discussed in your redox reaction, NiCO4, where the oxidation state of nickel is 0, FeCO5, oxidation state is 0. Ready? Oxidation state is 0. Fine. Write a point here. The metal have a back donation tendency. The metal have a back donation tendency. Metal have a back donation tendency to the ligands. And that is discussed in your coordination compounds, okay? The synergic effect. So there is a back donation of electron from the metal to the vacant pi star orbital of carbon monoxide. Back donation tendency to the ligands. In bracket, pi acceptor ligand. And such, listen, this actually, there is a coordinate bond between central metal, transition metal and ligand. Okay, that's a coordinate sigma bond. In addition to that, if there is electron in a orbital of d orbital of transition metal, and here we have pi star orbital of carbon monoxide, then there will be a back donation to form a pi bond. Okay. So the metal carbonyl bond have a pi character, a double bond character, and that is by the back donation of electrons from the orbital of metal to ligand. And this is discussed in your coordination compounds with a detailed picture and view. Okay, so will be discussed there already. And the ligand CO, which accept a pi electron, from transition metal. So that's why the ligand is known as pi acceptor ligand. Okay, that's why the ligand is known as pi acceptor ligand, pi electron acceptor ligand. Okay, so in the if the metal is in a lower oxidation state, there is a chance for back bonding from metal. That is the case, okay? Because if the metal is in a lower oxidation state, what happens? Metal have a lot of free electron in its orbital. Okay, because the electrons are not loosed. This is in a lower oxidation state. So that filled electron may have a tendency to form a bond. That is said to be back donation. So in the case of nickel tetracarbonyl, iron pentacarbonyl, generally in the case of carbonyls, metal exists in a lower, very lower oxidation state, say 0. So there the metal have a small tendency for a back donation, okay, to the ligand, and the ligands which accept the back donated electron from metals are said to be pi acceptor ligand. Okay, just a point which is given in your textbook. Low oxidation states are found in when a complex has a ligand capable pi acceptor character. in addition to the bonding. Low oxidation states are found when a complex has ligands capable of pi acceptor ligand. So usually metal which exists in a low oxidation state means when the metal is in contact with the pi acceptor ligand. Okay, that's a point. Ready? So metal have a back donation tendency to ligands. Ready? And in bracket ligands means ligands called pi acceptor ligand. Pi acceptor ligand. Okay, close the bracket. Fine. So that's all about oxidation state. Next we have to discuss trends of stability in oxidation state. Okay. Next topic, the stability of higher oxidation state. The stability of higher oxidation state. The stability of higher oxidation state. Okay. Usually the higher oxidation state of a metal or anything which is satisfied by the more electronegative element like fluorine and oxygen. Okay. The higher oxidation state of any elements are usually satisfied by more electronegative elements. Higher oxidation, for example, if manganese is in a +7 oxidation state, and this +7 can be satisfied by a surrounded more electronegative element like fluorine and oxygen. In all compound, that is a general trend. Okay, more electronegative element can satisfy the higher oxidation state of a typical metal. Okay, so we want to discuss the stability of stability of higher oxidation state. Okay, so your transition metals will be more stable in higher oxidation state if the surrounded one is fluorine and oxygen. Ready? If the surrounding atoms are fluorine and oxygen, then your transition metal have a greater existence in the higher oxidation state relatively. Ready? So first point, usually that's a general concept. Okay, usually higher OS are occupied by more electronegative fluorine and oxygen. More electronegative fluorine and oxygen. Ready? More electronegative fluorine and oxygen. Okay. Next point. In case of manganese, listen. In case of manganese, it can only surrounded by, but the manganese, in case of manganese, it is surrounded by, usually it is surrounded by 4 members. 4 members. Okay, so MnF7 not possible. Okay, so the higher oxidation state of manganese not satisfied by what? Fluorine, but it can be satisfied by oxygen. Okay, and what is the reason that we can say that? Due to the ability of oxygen to form multiple bond. Ability of oxygen to form. Here also 4 oxygen, right? Manganese can surround what? 4 atoms at a time. Okay, but if it is 4 fluorine, what happens? The charge will be +4, not to the higher one. Okay, but if it is 4 oxygen, oxygen have a ready tendency to have multiple bond. So every oxygen creates what? +2 charge. So relatively the oxidation state increases. Okay, usually the higher oxidation state satisfied by fluorine and oxygen, but in case of manganese or compounds like that, fluorine is not able to form what? Or not able to satisfy the higher oxidation state compared to oxygen. Then why the oxygen have a capacity to satisfy the higher oxidation state means oxygen can form multiple bond at a time. That's the explanation. Okay, next point. In case of manganese, this is a typical point, okay. In case of manganese, usually surrounded by 4 atoms or 4 members, okay. Close the bracket. In case of manganese, the fluorides not able to satisfy the +7. The fluorides not able to satisfy the +7. Okay, what is the reason? Not able to satisfy the +7. Why? Why it is so? MnF7 not possible. MnF7 not possible because MnF7 not possible. Not possible. Okay, but oxygen can. Okay, continue the point. But oxygen can. Ready? Oxygen can. Listen. Examples. Oxygen can satisfy the higher oxidation state. Okay. Example: MnO3F. MnO3F. Ready? MnO3F is an example where manganese is in +7, where they're surrounded by 4 atoms. Till it is 4 atoms. Okay. And Mn2O7. Manganese is in +7. Okay, so the higher oxidation state of manganese can only satisfied with the help of what? Oxygen. That's the point. Okay, not only by fluorine, it requires what? Oxygen. Why the oxygen have an advantage means? Oxygen have, or oxygen can form multiple bond. Hence can satisfy. Okay, that's the point. Ready? So in case of manganese, MnF7 not possible, or the higher oxidation state not satisfied by fluorine. Okay, because if it is satisfied by fluorine can form a single bond at a time. Okay, so if it is satisfied by fluorine, it will be MnF7. But unfortunately, manganese can adopt 4 atoms. Ready? So with the help of fluorine, moreover with oxygen, there may be a chance for +7, or with only oxygen, there is a chance for +7. And the advantage of oxygen, that is, it can form multiple bonds. Okay, so minimum number, maximum oxidation state by means of multiple bond. Ready? In Mn2 oxygen, there is a bridge bond. Bridge MnO bond. Bridge bond. Okay. So show it. Okay. NCERT discussion. In Mn2 oxygen, there is a bridge bond. Next. TiX4 stable, but for vanadium and chromium, VF5 and CrF6 only stable. And this X may be what? Fluorine, chlorine, brominated. TiCl4 is stable. Here in this all case, the oxidation state is maximum, right? +4. Here is +5. Here is +6. Okay. So the maximum oxidation state of titanium can be satisfied by any halogen, no problem. Okay, oxygen can do, no problem. Oxygen can form TiO2, no problem. But the maximum oxidation state of vanadium, if it is satisfied in terms of halogen, then the halogen should be fluorine. But in the case of manganese, it is not possible for fluorine. Okay, so show this one also. Okay. Beyond manganese, next point. Beyond manganese means after manganese. So simply we discuss the case of scandium. It only shows +3, okay. So it is only stable in the case of oxide. Sc2O3, Sc2O3, okay. Where in the case of titanium, the valence higher oxidation state can be satisfied by any halogen or oxygen. In the case of vanadium, chromium, it is only satisfied higher oxidation state, can be satisfied oxygen, you know, V2O5, Cr2O3. Oxygen can do, no problem. Okay, because oxygen have an extra advantage compared to fluorine. Ready? Moreover, vanadium and chromium where the oxidation state, higher oxidation state can also satisfied by fluorine. But in the case of manganese, it is not okay. But it can be with the oxygen, with the help of oxygen. The next, beyond manganese. Beyond manganese, only the maximum possible oxidation state, that is higher oxidation state, is +4. Okay. Sorry, +3. Now, so next point, write the next point. Beyond manganese, no metal trihalide exists. No metal trihalide exists except FeX3 and COF3. Okay. Where the beyond manganese, what are the oxidation state, maximum oxidation state? +4, +6. In case of iron, it may be +6, but it is a rare one. Okay, +6 is a rare one for iron. Okay, so the maximum chances for +4, but it is only in the case of oxygen. NiO2, it is +4. In case of nickel, can show what? +4, but it is with the oxygen. COO2 +4, but it is with the oxygen. Okay. Beyond manganese, if the higher oxidation state is satisfied by halogen, then it is only found in iron and cobalt. Okay. So the point, that is beyond manganese, no metal trihalide exists. Any other metal trihalide not exist. Only FeCl3, FeBr3, like that. Come CF3. Okay. Dihalide may be possible, but trihalide, moreover tetra, not also possible. Okay, fine. The next point. Next point we already discussed. Copper disproportionation discussed. Copper disproportionation discussed. Dioxide next point, the highest oxidation state in oxide, the highest oxidation state in oxide equal to the group oxidation state up to manganese. Up to manganese. And you know, listen, so oxide have not much limitation, only fluoride have some limitation. Okay, oxide is much flexible. So the point, the scandium is in +3, titanium is in +4, vanadium is in +5. These all are stable compounds. Okay, chromium is in +6, manganese is in +7. Okay, so the highest oxidation state in oxide up to manganese is equal to the group oxidation state. You know, this group is third one, right? This is the third group, fourth group, fifth group, sixth group, seventh group. So the group oxidation states are +3, These are the group oxidation state. Okay, so that is the point. The point is the highest oxidation state in oxides will be equal to the group oxidation state up to manganese, not up beyond manganese, up to manganese. Okay, so we can show this one. And this is a meaning, which means these all are stable, right? Nickel dioxide is next point. Beyond manganese, the most common higher OS is beyond manganese. The most common higher OS is +3. They are given to us +3. Okay. Bracket Fe2O3. NiO2 existing on, but according to your NCERT, it is NiO. Okay. So beyond manganese, the higher oxidation state is +3. In case of oxygen, example Fe2O3. Okay. Next, but in FeO4, FeO4 to minus. FeO4 to minus. What is oxidation state of iron? FeO4 to minus +6. But in FeO4 to minus, in bracket Fe in +6. But readily decomposed to Fe2O3 and O2. Okay, there is a chance for existence of +6 in the case of iron, but it is not a stable compound. It readily decomposes to Fe2O3 and O2. Okay, so the point is that beyond manganese, according to your NCERT, beyond manganese, there is a chance for existence of +3. The maxima is +3, and it is mainly found in your Fe2O3. Okay. Next point. If metal oxide is in a lowest choice, if metal oxide in lowest OS, basic. If metal oxide in lowest OS, basic. They have a if a metal exists in a if a metal exists in a lowest oxidation state, the compound will be ionic. If a species is ionic, it have a tendency to become a base. If this is an oxide, then it will be a basic oxide. Okay, so if metal oxide in a lowest choice, then it will be ionic come basic. Ionic, the term it is already discussed. Okay, basic. Example MnO, FeO, TiO. Okay, next point, if it in intermediate OS, if it is in an intermediate OS, it is have a amphoteric character. Okay, if it in intermediate OS, will be amphoteric nature. Amphoteric. Example, Cr2O3, Mn2O3. Cr2O3, that is actually +3. +3 is the intermediate state of chromium. Mn2O3 +3. They all are intermediate state of manganese. Okay. But Sc2O3 is not amphoteric. Okay, that is the highest oxidation state of scandium. Next point, if it in highest oxidation state, highest choice, if it is in highest choice, If it is in highest choice, acidic. Example, CrO3. Example, CrO3. Some CrO3, Mn2O7, like that. Okay, very same concept we are going to repeat ചെയ്യുന്നുണ്ട് ചില ടോപ്പിക്സിൽ. Enough. Cr2O3, Mn2O7, etc. And you are familiar with the mixed oxide. It is discussed in redox reaction, mixed oxide. Mixed oxide. So put it as a note. Mn3O4, CO3O4, Fe3O4 are mixed oxides of transition metals, and this is a compound with a special oxidation state. Okay, so this is discussed in redox reaction. Anyway, it is given in your textbook. Mn3O4, CO3O4, Fe3O4 are mixed oxide. Mixed oxide means this is a combination of MnO, Mn2O3. This is a combination of CaO, CO2O3. It's a combination of FeO, Fe2O3. Okay, that is the concept of mixing. Okay, mixed oxide. Ready? So do some questions. Ready? Question number 1. Okay, please pick the questions. Okay, question number 1. 3, 4, 5, 6, 12, 14, 15, 18, 20. Okay. 22, 23, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 39, 41, 42, 43, 48, 49, 49 വേണ്ട, no need of 49. 50, no need of 50. 52, 54, 65, 64, 67, 69, 71, 75. Okay, so do the questions. Finished. Okay, ready? Relatively simple questions. Okay. So next topic, potassium dichromate. 2 or more topics in your D block. Okay. Potassium dichromate, K2Cr2O7. Potassium dichromate, K2Cr2O7. Potassium dichromate, K2Cr2O7. Ready? And this is prepared from chromite ore. Chromite ore. So the extraction or the preparation of dichromate is from chromite ore. So first point, prepared from chromite ore. Chromite ore. Okay. Chromite ore. FeCr2O4. Chromite ore, O-R-E, or FeOCr2O3. Ready? And this is also known as chrome iron. Chrome iron or ferrochrome. Ferrochrome or chromite ore. Okay. So show this one. Okay. So moving to the preparation. So this is prepared from this ore. And the ore is known as chromite ore. It may be in this form or in this form. Okay. Ferrochrome or chrome iron, alternate names are. So preparation consists of 3 steps. Okay. The first step, that is, we have chromite ore. Okay. In presence of an alkali, it undergoes, or the ore is roasted. The ore is roasted within a reverberatory furnace. So furnace used for roasting. Okay. In presence of alkali like NaOH or Na2CO3 to form sodium chromate. To form sodium chromate, NaCrO4. Okay, so that's the first step. So write a small description. Roasting of chromite ore. Roasting of chromite ore in reverberatory furnace. Roasting of chromite ore in reverberatory furnace. Reverberatory furnace. Okay. In presence of reverberatory furnace in presence of alkali like NaOH or Na2CO3. NaOH or Na2CO3. Okay. So we have FeCr2O4. Ready. Which on treatment with the which on roasted. Roasting means reaction in the presence of oxygen. Okay. Either in presence of NaOH or in presence of Na2CO3. And products are sodium chromate plus Fe2O3 plus H2O. Okay, here it is also sodium chromate plus Fe2O3 plus CO2. See the difference? Okay. If NaOH, H2O, that's the difference. Ready? Both are applicable, and this is given in your textbook. Okay, so just a roasting in presence of an alkali. So the aim is to produce sodium chromate. Okay, so no need of studying with the balanced stoichiometry. You have to know the components. Okay, no need of studying with the balanced stoichiometry. This is objective. Stoichiometry is given in the textbook. Okay. So that's the first step. what? Preparation of chromate. Okay, and the next step is we want to convert this chromate into dichromate. Ready? In presence of acid. So next step, step number 2, acidification of sodium chromate to form sodium dichromate. Acidification of sodium chromate to form sodium dichromate. So no need of showing stoichiometry. Okay. So sodium dichromate, sodium chromate. This is sodium chromate. Okay, which is acidified in presence of, say, sulfuric acid or something like that. Okay, to form what? Sodium dichromate. Okay. Ready? Third step. Treatment of dichromate, sodium dichromate with the KCl. Treatment of sodium dichromate with the KCl. So the formed sodium dichromate, which is treated with the KCl. So there is an exchange reaction to form K2 Cr2 O7. Okay, and then properties. Properties. Some physical properties are given in the text. Properties. They are orange crystals. Multi-point ഒക്കെ ഉണ്ടായിരുന്നല്ലോ. Old NCERT ആണ്. Old NCERT. Old ആണോ? അപ്ഡേറ്റ് തന്നെ പഠിക്കണ്ട. Multimoin ഒന്നും പറയുന്നില്ല. So no need of studying. Okay. So orange crystal. Next point. In basic media turns to chromate. In basic media turns to chromate. So there is an interconversion equilibrium. Listen. CrO4 2 minus, which can convert to what? Cr2 O7 2 minus if the medium is acidic. This is chromate, which is in presence of acidic medium forms dichromate. Now we are writing the property of dichromate. So dichromate on basic medium forms what? So the reverse reaction should be in a basic medium. Okay, so dichromate in basic medium forms chromate. So the point is, in basic medium they turns to chromate. So there is an interconversion actually, like this. Show this one. Okay. Next point. There is an extra point. Okay, not in your textbook. But maybe in some questions or in another chapters. Okay, test for H2O2. Test for H2O2. H2O2, you know, hydrogen peroxide. That's a compound you have to know. That is discussed in your hydrogen, and we can use we can choose a test for H2O2 in terms of K2Cr2O7. K2Cr2. So if you have K2Cr2O7 along with the H2O2 with the sulfuric acid, what happened means the orange colored, this orange one, right? The orange colored K2Cr2O7 become blue colored CrO5. And the CrO5, the structure is discussed in your perchromic acid, butterfly structure. This is discussed in redox reaction, okay? Okay, discussed in detail, ready? With oxidation state of +6. Okay? So, when there is a presence of this peroxide linkage is formed by the presence of hydrogen peroxide with dichromate. Okay, so the orange colored dichromate is turns to blue colored, means that indicates the presence of hydrogen peroxide. So this is a test of hydrogen peroxide which is in terms of your dichromate. Okay, so put it as a note. Okay, another test for chloride ion. Test for chloride ion. Test for chloride ion. And that is, the test is known as chromyl chloride test. Chromyl chloride test. Similar to this one, okay? We have K2, orange colored K2Cr2. Ready? Which one treatment with the chloride ion salt, for example NaCl, like that, with the sulfuric acid. So that in presence of chloride ion, the dichromate turns to CrO2 Cl, said to be chromyl chloride. Chromyl chloride. Okay. And forms a orange red vapor. Orange red vapor. So chromyl chloride test is for Cl minus ion. Okay. The next is structure. Structure. Number 1, CrO4 minus. CrO4 minus. Chromate is, I think, a yellow colored one, right? CrO4 minus. So yellow colored ion due to LMCT. Okay. Even the chromium is in +6 oxidation state. This having a color. The configuration is D0, but having a color due to LMC, and have a tetrahedral shape. This is the color of chromate ion. Sorry, shape of chromate ion. Show that. The two oxygens have a negative charge. Okay. Any of two oxygens have a negative charge. The next, the color of, sorry, structure of dichromate. Structure of dichromate. Dichromate have, next, dichromate. Dichromate, give a small description. There is a bridge bond, okay, fine. So, have tetrahedral structure with a common sharing of a corner. Common sharing of a corner. Common sharing of a corner. That means a bridged. Common sharing of a corner. So this is a tetrahedral shape. Listen. This shape is something like a tetrahedral. Okay, but this is a commonly shared oxygen. Tetrahedral shape with a common shared oxygen. And the bond parameters are given in the textbook. Compulsory. It is compulsory that you have to study the bond angle 126. Okay, bond length are also given 179 picometer and 163 picometer. 163 picometer. So the two bonds are, there are two different bonds. Okay, this is a bridged CRO bond and this is a normal CRO bond. They are entirely having different bond dimension. Okay, and this is, you know, having a color of orange. Ready? So you know that dichromate is a good oxidizing agent and it is used as a primary standard oxidizing agent in volumetric analysis. And the titration using dichromate is said to be dichometry. Okay, so next point, used as a primary standard oxidizing agent. Used as a primary standard oxidizing agent. Used as a primary standard oxidizing agent in volumetric analysis. Ready? Volumetric analysis. In volumetric analysis. Okay. Next point. In acidic medium, reduced to CR3 plus. Okay, and the half reaction is discussed in redox reaction. Okay, this is a half reaction which is discussed. Okay, in acidic medium, this is the half reaction of the reduction of chromium. Chromium, what happens to chromium from +6 to +3 reduction, where the dichromate act as oxidizing agent in acidic medium. Okay, this will be the reaction where the product is CR3 plus. Okay, and it can oxidize I minus to I2. This is the half reaction of dichromate. It can oxidize what? I minus to I2. So this brings a half reaction. And you know how to solve a half reaction. And that is discussed in redox reaction. So dichromate is a powerful oxidizing agent in acidic medium, only in acidic medium. Okay, reactions are not observed in basic medium. But in the case of the next compound, potassium permanganate, the reactions are observed in acidic and basic medium. Okay, or neutral medium like that. Okay, here only in acidic medium. If the dichromate acts as a oxidizing agent in acidic medium, the dichromate itself produces to CR3 plus. Fine. Now let's check which of the following species will be oxidized in presence of dichromate. First one, iodide to iodine. The next one, bromide to bromine. Okay. The next, chloride to chlorine. Okay. Next, hydrogen sulfide, which means sulfur is in -2. This becomes sulfur. Okay, hydrogen sulfide to sulfur. Next, sulfur to sulfur dioxide. Next, SO4, SO3 to minus, sulfite to sulfate. Okay. Next, thiosulfate, S2O3 to minus, to sulfate. Nitrite, NO2 minus, to nitrate. Okay. Stannous ion, SN2 plus to SN4 plus. Ferrous ion, Fe2 plus to ferric ion. Oxalate, Cr of 2 minus to CO2. Okay, these all are the different types of reaction. Oh. Okay, and you know how to balance the two. Ready? Okay, and that is discussed in your redox reaction. No need of balancing here. Okay. I think you know how to balance this. Okay, here the number of electron lost is 2 electron, and this is half reaction of chromium. In order to add these two, this is gained 6 electron, but this is lost, so you have to multiply this with 3, then you can add with the first. So obtain the overall reaction where electrons get cancelled. Okay, fine. But before that, you have to know if your tin is oxidized, what is the product? Okay, this is important. If iodine is oxidized, iodide is oxidized, the chance is for I2, IO3 minus. Iodine, this is in -1 oxidation state, okay. Iodine can exist in a +7. So to where the oxidation taking place, that is important. That's important. Okay. So this sequence is important. Ready? Not about the balancing. Balancing is not important here, but here the sequence is important. Stannous to stannic, ferrous to ferric, oxalate to carbon dioxide, sulfur to sulfur dioxide, sulfite to sulfate, thiosulfate, and these compounds are discussed in redox reaction. Okay, exceptional oxidation state, a molecule with exceptional oxidation state, thiosulfate to sulfate, nitrate to nitrate, like that. Okay, hydrogen sulfide to only sulfur. Okay, if it is in a basic medium, it becomes SO2. Means in basic medium, usually the oxidation extended to more. Okay, in basic medium, iodide become IO3 minus. IO3 minus. Yes, 2 minus become SO2. But your dichromate, the reaction is only in presence of acidic medium. Ready? So that's all about dichromate. Then some uses are there. Okay. Usually. So write some uses. For the preparation of chrome alum, for the preparation of chrome alum, potash, you know potash alum, you know the structure of potash alum, K2SO4, Al2SO4 thrice dot 24H2O, potash alum, where if Al2SO4 thrice is replaced by Cr2SO4 thrice, that is said to be chrome alum. Okay, fine. Okay, Al2SO4 thrice is replaced by Cr2SO4 thrice, that is said to be chrome alum. So what will be the formula? K2SO4, Cr2SO4 thrice 24H2. Okay, chrome alum. Then chrome yellow in bracket, lead chromate is said to be chrome yellow, PbCrO4, and chrome red, chrome alum, chrome yellow. Chrome yellow is actually that's a common name which indicates the lead chromate. Okay, lead chromate, PbCrO4. The next is chrome red, that is PbCrO4.PbO, and these compounds all are prepared by using dichromate. Okay. Next, in oxidizing agent in organic chemistry, you know, dichromate is used as a acidified dichromate is used as a best oxidizing agent in organic chemistry for the cleavage of unsaturations. Okay, OA, oxidizing agent in organic chemistry. Then the next is volumetric analysis. That's a use. Okay, primary standard in volumetric analysis. Enough. Fine. Moving to the next. Potassium permanganate. The next compound. Potassium permanganate. KMnO4. Potassium permanganate. Okay. Like that. Potassium permanganate in bracket KMnO4. Here the ore is not chromite. It is said to be pyrolusite ore. Pyrolusite ore. So ore, pyrolusite ore. That's nothing but MnO2. Okay. So like your chromite ore, here is pyrolusite ore. MnO2. Okay, preparation. First one, first step, roasting of pyrolusite ore. In presence of alkali, bracket KOH or K2CO3, in presence of alkali, in bracket KOH or K2CO3, to form potassium manganate, Okay, potassium manganate is K2MnO4. Ready? So you have pyrolusite ore, which is roasted, the very same process. Okay, and it may be in presence of what? Like NaOH and H2CO3. Here it is KOH or K2CO3. Okay, and it become K2MnO4. Here also K2MnO4 plus here it is H2O, here it is CO2, plus Mn2O3 is the right, no, this much, it become K2MnO4, and this K2MnO4 is said to be potassium manganate. Okay, second step in your textbook. Okay, K2MnO4 is a dark green compound. Okay, dark green compound. The next method in your textbook, that is the disproportionation. Next step, disproportionation of K2MnO4. In neutral or acidic solution to form permanganate. Neutral or acidic solution to form permanganate. So there is a disproportionation. Okay. So here forms the manganate. This is potassium or simply manganate. The manganate where the manganese oxidation state is +6, and it become what? +1 and +4, which means it is disproportionated, so that you obtain permanganate. And this is how it is prepared, and is given in your textbook. Okay, show the reaction. Okay. But in a textbook, it is also given that commercially, for a commercial production, the first initially formed manganate. Initially, the manganate is formed by the reaction of pyrolusite or with KOH or K2CO3, so that there forms potassium manganate. And this may be in presence of any catalyst KNO3 like that, oxidizing in KNO3 like that. Okay, KNO3 or in presence of oxygen, both are enough. Okay, and the formed manganate, this is said to be manganate, dark green colored manganate, which is disproportionated in presence of acidic medium. to form permanganate, and this is simply a laboratory preparation. Okay, for a commercial purpose, the very same manganate which is prepared from pyrolusite ore, which undergoes electrolytic oxidation in alkaline medium. Okay, so it is electrolytically oxidized. Oxidized means it simply lost an electron. Okay, have 2 extra electron, right? If it simply lose an electron means what? It become MnO4 minus. Okay, this is how permanganate is prepared in commercial. The next structure. MnO4 2 minus and MnO structure. MnO4 2 minus. Tetrahedral structure. Tetrahedral. Okay. Next is MnO4 minus. It also have tetrahedral structure. The multiplicity of oxygens that depends on the number of negative charge. Okay, number of negative charge. If only one negative charge, it means one oxygen will be single, rest are double. Okay, there is no other change, and they are not mentioned the bond parameters, bond length, bond angle. Okay, this is only discussed, and the color, you know, purple color. Fine, that's all. Now we want to discuss the volumetric action. Ready? Next point. K-MnO4 act as strong oxidizing agent in any medium. Strong oxidizing agent in any medium. Okay, in any medium. Ready? Number 1, acidic medium. Number 1, acidic medium. Acidic medium. Number 1, acidic medium. Acidic medium, the MnO4 minus, the reaction is, and acidic medium become Mn2 plus. Acidic medium become Mn2 plus. Okay, become Mn2 plus, and you know it is discussed already. In acidic medium, the reaction is 5 electron to form Mn2 plus plus 4H2. Okay, this is a reaction in acidic medium, and MnO4 minus from plus 7 it reduced to plus 2. Okay, and it can oxidize all species which is oxidized by K2Cr2O7. Which is oxidized by? Can oxidize all which is oxidized by K2Cr2O7 in acid. The very same. Okay, that already discussed. Ready? The very same reaction. So next point, can oxidize all species. So this is a half reaction in acidic medium. Okay. So half reaction in acidic medium. Now we wanna write the reaction, but it is already written in terms of K2Cr2O7. So for a connection, you simply add a point. Can oxidize all species which oxidized by K2Cr2O7 in acidic medium. Which oxidized by K2Cr2O7 in acidic medium. Okay. It is only in acidic medium. Okay. Okay. Number 2, in neutral or slightly alkaline medium. Number 2, neutral or slightly alkaline medium. Neutral or slightly alkaline medium. it can oxidize, sorry, in neutral or slightly alkaline medium, become Mn4 plus, become Mn4 plus, MnO4 minus plus Mn4 plus, right? 3 electron. This okay. Okay, example, I minus 2, IO3 minus, I minus 2, IO3 minus, Br minus 2, BrO3 minus, H2S2, H2S, 2 SO2, no. Next, in your textbook, next, in strong alkaline medium, become MnO4 minus, MnO4 2 minus, manganate, okay, it turns to manganate. Turns to manganate. Become manganate. The reaction is MnO4 minus plus electron become MnO4 2 minus. This is the half reaction. Okay. Examples are not given. Ready. Uses. For bleaching wool, cotton, silk, etc. For decolorization of oil, in organic chemistry, next step, that's enough. Put it as a note, NOD note. A point which is given in your textbook, okay, not the outside point. In volumetric analysis using KMnO4, hydrochloric acid is not used to acidify, are not used for acidification. In volumetric analysis of KMnO4, hydrochloric acid not used to acidify. Reason? Reason? You know that chloride ion may be chloride ion may be oxidized to Cl2. Okay, so if you are using hydrochloric acid, there is a chance for this oxidation. Okay, but the purpose is actually for acidification. Acidification means supply of H+. Okay, the purpose of HCl, that is to supply H+. But unfortunately, MnO4 or KMnO4 minus may oxidize what? Cl minus. Okay, so it is not used for acidification. Ready? The reason? In bracket, the reason? KMnO4 may oxidize chloride to chlorine, Cl minus to Cl2. Okay, Cl minus to Cl2. Ready? One more not point. Potassium K2Cr2O7 and KMnO4. K2Cr2O7 and KMnO4 on heating decompose to form oxygen. K2Cr2O7 and KMnO4 on heating decompose to form oxygen. Okay, so K2Cr2O7 heat, it becomes K2CrO4 plus Cr2O3, where oxygen may evolve. Like that, if you have KMnO4, which on heating, the K2MnO4 plus MnO2 plus oxygen. So both your K2Cr2O7 and KMnO4 on heating may evolve oxygen. Okay, now fine.